Page 503, proving the Pythagorean theorem, but this time through similar triangles. I've got protractor, highlighter, ruler, pencil, etc. And let's get into it. You can use the right triangle altitude similarity theorem to prove the Pythagorean theorem. Reminder, the Pythagorean theorem says on a right triangle, leg A squared plus leg B squared equals C squared. That tells us the distance. We've also used that when we did the distance formula earlier in this curriculum. Use the diagram and follow the steps to prove the Pythagorean theorem. Given this is a right triangle and angle C is the right angle. So from that information, we're going to be able to say that AC squared plus CB squared equals AB squared. That's this notation. Always, which hasn't really been mentioned till now, so mark the calendar, that across from angle A is side little a. And across from angle B is side little b. And across from angle C is side little c. So I didn't put anything more than like one mark there and two marks, angle markers there, because they're meant to be different, but they're not boxes, because only C is the right angle. And across from angle C, that deserves a highlight, across from angle C, which is 90, is the hypotenuse. And so that is what we're acknowledging, that the right angle has to be there, and then our sides actually create the Pythagorean theorem. Here we go. Construct altitude CD. That's what this entire lesson has been about when we talk about geometric mean. It's about creating an altitude on a right triangle, and then because of the relationship of similar triangles inside right triangles, we end up having, geometric mean relationships. And so we can use that fact. I lined it up. I made a right angle here, and that's point D. There it is, CD. In fact, continuing to highlight, I'm going to highlight CD yellow. Because we have right angle relationships and we have similar triangles, we get to do all of this. And it's all based upon the idea of proportions in similar triangles. Write a proportional statement to describe the relationship between the longest side and the hypotenuse of triangle ABC. So ABC is all of this, and CBD. So CBD, it's a little one. We should be able to spot the long side, short side, hypotenuse within those triangles. Then write the proportional statement as a product. So we need to, we'll do that part secondly. So here's the first part. The first part is I'm going to write the longest leg and hypotenuse of triangle ABC. So we had this format from before, a couple of yellow pencils. We had long leg, and then we have hypotenuse. So in triangle ABC, the long leg is BC. And the hypotenuse is AB. I like this structure over here on this side, by the way. Long leg and hypotenuse kind of keep things organized. So then when I only look at this triangle, the long leg is BD. And the hypotenuse is BC. There it is, using the same segments from two different triangles, and yet the same segment because the triangles overlap. We have a geometric mean problem. So I can write it like this. I can do rewrite the proportional statement as a product. They mean cross multiply. I don't like saying that. It loses algebraic like problem solving, understanding, but it is. It's cross multiply. So that means that BC times BC, or BC squared, and then AB times BD. So one of the things we did with geometric mean in solving this, and go watch one of the short videos where I show how I solve that, we do use this concept of x squared, and this is BC, and that quantity is squared, and it's multiplied by the two side lengths that it's opposing. Then rewrite a proportional statement to describe the relationship between the short leg, so short leg, and the hypotenuse of ABC, and now the other one, ACD, this one. Okay, so short leg to hypotenuse of the big triangle, ABC. So short leg here would be AC. And the hypotenuse, so of the big triangle, the hypotenuse is the longest side. It's across from the 90-degree angle. It's AB. Now, since it's a proportion, we have to write the fraction that it equals. And in the smaller triangle, triangle ACD, that means the short leg is just this one. It's just AD. Again, short leg, hypotenuse. You don't see that down there. Short leg, hypotenuse. AD over AC. Oh, and there it is. AC is being used twice. So AC, just like geometric mean has been about, you're going to have something that's in the top of one fraction while at the same time the bottom of the other. Then it says write the proportional statement as a product and cross multiply. So AC squared, because when you cross multiply, you're going to take AC times AC, and that is AC squared. And then the other two, AB times AD. AB times AD. Okay, so if we have an equation, a property of equations that we actually studied back in the second module was addition property. And if I look at one part D, it says add the statement in part B to the statement in part C. So I'm going to add BC squared plus AC squared because they're on the left side of the triangle or the equation. And then on the right side of the equation are these other statements, and I'm going to add those together. So it'll look something like this. I'm going to have BC squared plus AC squared, and then it's going to equal, that's these two things added together that are on the left side of the equations. Just adding them straight down, there's an equivalence. Over here, we have the right side of the equation. We're going to add those together. So I'm going to have AB, BD, plus, addition property of equality, AB, AD, because those are the two sides on the right side. They add together, and the equation remains balanced. Now, this right here, do you recognize that AB is all of this? It's broken up into AD plus BD. This right here and this right here can be rewritten so that the AB is factored out. And a process from algebra, thank you algebra for giving this to us. If we have a multiplication, so there's a times between those two things, and another multiplication, there's a times between those two. If they have something in common, that is called a factor. And we're going to factor out through something called the distributive property, or the opposite of the distributive property. But we're going to factor out what they have in common, and it will look like this. Equals, I'm going to rewrite this here in a second, AB times BD plus AD. And then over here, BC squared plus AC squared. This right here, this one, in fact, it probably deserves some highlight, and I'm going to bring in a different color entirely. Let's go green. This AB is because it came from two locations when we added these two together. So, E is done. Now let's go F. What is equivalent to AD plus DB? AD, DB, if you add them together through segment addition postulate, AD plus, well, I have it written BD here, so I'm going to switch that around. BD. I mean, it's just the order of the letters. But what is equivalent is the whole line segment AB. This is AB. All of that. And if you have AB times AB, then that means AB times AB could be rewritten as AB squared. And all the way back up at the top, AC squared plus CB squared. I think I wrote that as BC. I switched that around. The letter, switching. But if you have AC squared plus BC squared, it equals AB squared. This is the final part that's going to substitution allow us to rewrite the Pythagorean theorem. BC squared plus AC squared equals AB squared. And there it is, A squared plus B squared equals C squared. That's clean. That might not be visible and immediately available to you right now in the moment, but that is a really clean proof of the Pythagorean theorem. Solid. Thank you for watching this video. Thank you for watching this episode. I hope you had some good information that you were able to gather from it. We have one more video from this lesson. Lesson 4 is what we're currently focused on. It's Talk the Talk, and that's on the next page, so stick around for the information we're going to discuss there. Thanks for watching. See you in the next episode.